Hello everyone, welcome to Chapter 7. This is the first part of Chapter 7, and in this is where we're going to actually look at chemical reactions and how we define those quantities and how we account for what's going on is in balancing of these reactions. So remember way back we talked about the difference between a physical and a chemical change. A physical change alters the state, that it's like going from liquid water, boiling it into vapor, or freezing it and taking it to ice. A chemical change, though, alters the actual composition of whatever the material is. And so whatever it was, it is now something different. And so the example here is iron atoms going to iron oxide when a nail rusts. So when we have chemical reactions, we are going to be showing you what's actually going on with the molecules, and we're also still going to account for whatever the physical changes are that occur, such as gas, liquid, etc. So we by convention write the reactants on the left-hand side of an arrow, and then the products are on the product side. And I think of this as reactants react to produce products. Okay, so reactants react to produce products. And so we write a statement that tells us what we started with and what state they were in, and then what happened after we reacted them. What are they now considered to be? So did they change chemically? Did they change states and things like that? So we use a chemical equation to do this, and so this gives us the molecular or ionic formulas of the reactants and the products. As I said, it also gives us what the state is, and so we put that in parentheses with a G for gas, an L for liquid, S for solid, and AQ for aqueous. We put the relative number of molecules that are required, and this is synonymous with moles, so you can consider that to be the number of moles that are required. And then we use that to determine the weights of the reactants. So this is what engineers call a mass balance. We have to use the molar ratios that they are reacting by to figure out how many pounds or kilograms or whatever we started with and we ended with. So the amount of each substance used and made is accounted for, and it has to follow the law of conservation of mass, because ever how many carbons you start with, you have to have that many carbons when you get done. Ever how many hydrogens, you have to have the same number of hydrogens in the reactants and the products, and so that's because you can't create a new one. You can only rearrange them. Okay, so when you rearrange them, we balance those equations by balancing the number of atoms / the number of moles. So this process is called stoichiometry. Stoichiometry, okay, and this accounting for the balance between the two, and that it reacts in mole ratios, okay, because everything is based on the mole, not on grams, because the moles, there are different numbers of grams in each mole of different substances. Okay, so I've got a little example here just kind of showing you how we equate. We've got 1 carbon on both sides, 4 hydrogens on both sides, 4 oxygens on both sides. So when we balance an equation, what I do is I set up an inventory basically. So what I do is I look and I see what are all the elements that I have. So I'm going to balance this equation with cobalt 3 oxide and solid carbon. Solid carbon is elemental carbon. That's how it exists in nature. Okay, and we're going to produce solid cobalt metal and carbon dioxide. So over here I have cobalt. So I'll have cobalt on this side. I have oxygen. So I have oxygen on that side. And then I have carbon. So in order to balance this, what I'm going to do is, first of all, I'm going to look and I'm going to say, okay, if I have something by itself, I can multiply that by whatever I need to make it balance at the end. So typically what I'm going to do is I'm going to look at things that are not like that. Things that I know are going to be adjusted when I put a number, because the only thing I can do is add a coefficient, because I can't change the formulas because that's what's happening. So I can only put the coefficient, and those are the numbers, if you recall, at the beginning of these numbers, of these elements. Okay, so I have 2 cobalts. So I'm going to write my initial inventory here. I've got 2 cobalts on this side and 1 on that side. I have 3 oxygens on this side, and I have 2 oxygens on the product side, and then I have 1 carbon on the reactant side and 1 carbon on the product side. Now, when I look at this, I've got these numbers are not the same, and they have to be the same. So what I'm going to do is I'm going to multiply the entire molecule by a number to try to get these numbers to be the same. Now, when I see something and I see a 3 and a 2, okay, that automatically tells me that I'm probably going to have to multiply the 2 by 3 and the 3 by 2 to get that least common denominator, right? So if I see that right off the bat, that's what I'm going to do, okay? Now, in order for me to do that, I'm going to have to multiply this molecule by 3, because then that's 3 times 2 is 6 oxygens, but it also affects the carbon, and I now have 3 carbons, okay? Over here, I've got 3 oxygens. I now have 6. I'm going to multiply that by 2, which is multiplying this whole thing by 2 to make 2 times 3 is 6. So those are now balanced. I now have 4 cobalts, right? So I need my cobalts to be the same. Cobalt is by itself, so that's not a big deal. So I can multiply it by 4, which now gives me 4 cobalts, and that makes those equal. And the last thing is my carbon. I have 3 carbons over here. I need 3 carbons on the reactant side. Luckily, it's by itself, so if I multiply that by 3, it doesn't affect anything else. And now I am balanced because I have 3 carbons on both sides, 6 oxygens on both sides, and 4 cobalts on both sides. So you have one to practice. So a combustion reaction is kind of, it's just like what we did, except it's usually got one more step. All right, and I'll show you what I'm talking about. All right, so we're going to combust butane. Butane is C4H10. And if you recall, what a combustion does is I have to add oxygen to that, and then I'm going to form CO2 and water, right? And so it told me that's a gas. I know oxygen's a gas, CO2's a gas, and so this may be liquid or it may be gas. It says gas, tells me in the problem, because it could be either. So if the problem tells me, that helps. Okay, so everything is gas, starts out as gas, converts to gas. This is combustion, okay? Always you add oxygen and you produce CO2 and water if you have what we call a hydrocarbon, something with just carbons and hydrogens in it. Okay, so in order to balance this, I'm going to do the same thing. I've got carbon, hydrogen, oxygen, carbon, hydrogen, oxygen. The difference is, in a combustion reaction, I have oxygens in 2 places here on the product side. So when I take account of that, what I'm going to do is I'm going to say I have 2 plus 1 equals 3. Because when I'm balancing, I may change one and not the other. So over here I have 2 oxygens. I have 10 hydrogens. I have 2 hydrogens. I have 4 carbons on the left, and I have 1 carbon on the right. Okay? So you can really start pretty much however you want to. typically on a combustion reaction, I start with whatever is not a hydrogen or an oxygen. I do those last. So you do the H's and the O's last. So so the first thing I see is carbon. So if I put a 4 here, that gives me 4 carbons, and then it changes my first oxygen. Instead of 2, I now have 2 times 4 is 8. So now I have 8 plus 1 equals 9. So that balances my carbons. All right, and then I have 10 H's. So if I want to get 10 H's on the product side, the only thing I can do is multiply this whole thing by 5. So 5 times 2 is 10 hydrogens, and that now gives me 5 oxygens. So 8 plus 5 is 13, I think. Okay, so that's 13. So I've got 2 over here and I've got 13 over here. Now my hydrogens and my carbons are balanced. The only thing out of balance is this weirdo looking thing here. So I've got 13 on the product side and I've only got 2 on the reactant side. So I got to do something. So the easiest thing to do is if I multiply 2 times 13 over 2, okay, that cancels. That would give me 13 and that would balance. So if I do this, right, so I'm sorry, if I do this 13 over 2, right, 13 over 2 O2s, that gives me 13. That balances me. The problem is I don't really like to have non-whole numbers. So if I have a fraction like this is where that last step comes in. In order to get all of these numbers in my balanced equation to be whole numbers, to get rid of this 13 over 2, I'm going to have to multiply that whole thing by 2. Okay, so that will mean that I'll have 2 of those. I'll have 13 of these. I'll have 8 of those and 10 of those. All right, and so then I'm going to go back and I'm going to make sure that I have the same amounts on both sides. So I now have 8 carbons over here and I have 8 carbons over here, and on the left hand side I have 20 hydrogens, and over here I have 10 times 2 is 20 hydrogens. And then over here, I have 26 because I have 13 times 2, the 26. And over here, I have now 16 plus 10, right? So I have 26 oxygens over there. And I just went back and checked it. So see, it works. And if not, you can do it like going back and forth, back and forth, back and forth, but it takes forever, as you see, because for it to actually be balanced, it's going to be 2, 13, 8, and 10. So sometimes it'll ask you to write down like in a multiple choice. So you're putting the coefficients in the answer. So it would be 2, 13, 8, and 10, and that's the balance. So you see, it'd take you a while to get there if you had to, go back and forth and try to figure it out on your own. So this is really the best way to do it. Get it to where you have this fraction, and it'll be over 2 because you have O2, and so whatever you can multiply that by, you can get rid of that fraction, and you can have the balanced equation. And then you have ethane to practice on. So in strontium chloride, aqueous lithium phosphate, these are ionic compounds or polyatomics. And I show you this because when you have polyatomics, you're going to keep them together, because that way it saves you a whole lot of time. If you separate the oxygens out and all that, it'll take forever. So strontium chloride, SrCl2, and it said all of this stuff is aqueous, plus Li3PO4 is going to give us LiCl plus SR3PO4. Oh wait, SR3PO4 2. Sorry about that. Ran out of room. Okay, so we got to balance this, right? So the way I'm going to balance it is I'm going to have strontium, chlorine, lithium, and PO4 because I have PO4 on this side and I have PO4 on that side. So then I have strontium, chlorine, lithium, and PO4. All right, I have 1 strontium and 3 strontiums. I have 2 chlorines and 1 chlorine. I have 3 lithiums and 1 lithium. And I have 1 PO4 and 2 PO4s. See how that works? So I'm just doing that now. This was something where you had to take all of your skills. You had to be able to write the compounds, put them in there, and then we're going to balance the equation for them. Okay, so strontium, I have 1 over here, 3 over there, so I'm just going to start at the top. So if I multiply that by 3, that gives me 3 strontiums and it gives me 6 chlorines. For me to have 6 chlorines on the other side, I need to multiply that by 6. That now gives me 6 lithiums and 6 chlorines. So I've got that and that. And so my lithium over here, I need it to be 6. So I multiply 2 times, oops. I need lithium to be 6, so I'm going to have to multiply that whole thing by 2. Why is my pen not working? Okay. Trying to find my mouse. So I'm going to multiply lithium by 2. There it is, 2. I lost my pen. 2. So that gives me 6. And it also gives me 2 phosphates. 2, whoop, I can't see it, 2 phosphates, okay? And so now I'm balanced. So everything is balanced. So I have 3 strontium chlorides, 2 lithium phosphates, 6 lithium chlorides, and 1 strontium 2 phosphate. And done just in time. All right, so that is balancing equations.